The night the stars blinked wrong. What if the first clear sign of alien intelligence was not a message, but a shadow? It is 2 in the morning at a mountaintop observatory. The control room is dark except for the glow of monitors. On one screen, a single line of data crawls across the brightness of a distant star, point by point, night after night. An astronomer leans in, frowning, because the star has just blinked wrong. Normally, when a planet passes in front of its star, the light dips in a neat, shallow U shape. Tiny. Predictable. You can set your watch by the orbit. In the hunt for alien life, this is our bread and butter, regular, repeating shadows that tell us there is a world there. Perhaps even an Earth-like planet in a Goldilocks zone. But this curve is different. The star's brightness does not dip by 1%. It plunges by 20, then by 40. Then it stutters in a chaotic pattern that refuses to repeat on schedule. No simple circle of rock and ice can do this. The astronomer rechecks the instrument. No glitch, no passing cloud. The data hold. So the question comes, quietly at first, then louder. What if this time, it really is an alien megastructure, not a dust cloud, not a comet swarm, something built, not born? What if a distant civilization has wrapped its star in a vast swarm of machines, a Dyson-like system, harvesting almost all its energy, and we are watching its moving shadows play across the light? It should be noted that we have seen strange stars before. Tabby's star once dipped by more than 20% and sparked whispers of megastructures. Optimistically speaking, many of us wanted it to be artificial, but follow-up observations pointed to dust, not design. This means we have learned to be cautious, to exhaust every natural explanation before we even whisper the word alien. Now imagine a signal that survives that gauntlet. No dust model fits, no broken star can explain the pattern. Infrared telescopes see excess waste heat, exactly where it should be if colossal structures are absorbing starlight and radiating it away. At some point, we would have to ask if another civilization can shape structures on the scale of a star. What does that say about our place in the universe? Are we early, average, or already hopelessly behind? So, let's begin with that night in the observatory and follow the consequences. In this episode, we will unpack what astronomers actually mean by an alien megastructure, how such a thing would appear in real data, how the scientific community would test and argue, and finally decide, and how our world could change in the hours, days, and decades after a verdict. So it's time to find out the truth about what would happen if the stars really did blink wrong, why a shadow around a distant star could rewrite everything. So if a star really did blink wrong, why would that matter so much? There are a few discoveries that could hit harder than a confirmed alien megastructure, because it would not just be life, it would be power. In the hunt for alien life, we usually talk about microbes on Mars, or an Earth-like planet with oxygen in its atmosphere. Those would be revolutionary, but they would still be whispers, proof that biology can start, maybe even spread. A megastructure is different. This means intelligence has not only emerged, it has survived long enough, and cooperated strongly enough to reshape an entire stellar system. Think about what that implies. To build anything close to a Dyson swarm around a star, a civilization must control more energy than all of humanity has ever used. It should be noted that this pushes them toward a so-called Kardashev Type 2 level, tapping directly into stellar power. That is not just a new species. That is a possible future for us, staring back from across the universe. But while many of us quietly expect that life is out there, there is a problem. For more than half a century, we have pointed radio telescopes at the sky, listening for messages, and we have heard almost nothing. No clear beacons, no obvious cosmic greetings. This silence is wrapped up in what we call the Fermi paradox. If intelligent civilizations can arise and spread, why do we not already see their footprints everywhere? A true megastructure would be a strange kind of answer. No message. No greeting, just a shadow around a distant star that should not be there. A silent but deafening signal that says, yes, intelligence exists. No, it is not talking to you. However, reality is messy, and the data we collect is even messier. Stars flicker, dust clouds drift, instruments drift too. History is full of false alarms. The first pulsars were so regular that astronomers half-jokingly labeled one LGM-1 for little green men. Tabby's star, Kick 8462852, showed wild, irregular dips in brightness that did not look like any normal planet in orbit. For a moment, megastructures were on the table. So, let's begin to narrow this down. When we see a star dimming in a way that does not match planets, dust. or standard stellar physics, what do? Do we declare aliens, or assume there is some new natural process we have missed? The entire scientific method pushes us toward the second option. Optimistically speaking, an alien explanation is never the first choice. It is the last one standing after every natural hypothesis fails. So it's time to find out the truth about how close we have already come to that line, because in our own time, one very ordinary-looking star briefly seemed to host something extraordinary, and what happened next changed how we search for megastructures forever, from Tabby's star to tomorrow's mystery signal, and that brings us to one of the strangest light curves ever recorded. In the hunt for alien life, most stars look beautifully boring. Their brightness stays almost perfectly steady, with only tiny, predictable changes. But about a decade ago, buried in the Kepler mission's data, astronomers noticed a star that refused to behave. Its catalog name was KIC 8462852. We now know it as Tabby's star. What was wrong with it? Instead of the neat, shallow dips we expect when a planet passes in front and blocks a few percent of the light, this star plunged in brightness by up to about 22%. Sometimes it dipped a little, sometimes a lot, sometimes not at all. There was no clear period, no clean orbit, no simple pattern. For a while, it looked like the universe had thrown us a curveball. This means that, for the first time, serious astronomers had to ask a wild question out loud. Could this be an alien megastructure? A swarm of artificial collectors, like a partial Dyson sphere, could in principle pass in front of a star in irregular clumps, producing deep, chaotic dimming without the tidy rhythm of a single planet transit. It should be noted that this idea was never the default, but it was on the table. Then came the pattern interrupt. If this really was a colossal energy harvesting structure, it would not be invisible. All that captured starlight would have to be re-radiated as waste heat, glowing strongly in the infrared. So, let's begin to test the fantasy. Teams pointed infrared telescopes at Tabby's star, searching for that excess heat signature that a Type 2 civilization on the Kardashev scale should produce. They found nothing unusual. No giant infrared glow, no clear sign of a vast engineered system. Instead, as more data rolled in across different wavelengths, the picture shifted. Complex clouds of dust, perhaps from disrupted comets or fragments of material in a very messy system, could mimic those strange dips. Dust can block visible light efficiently while staying relatively cool, leaving only a subtle infrared trace. Optimistically speaking, the megastructure idea made a great headline, but the physics quietly pointed elsewhere. Tabby's star became a case study in how science actually reacts to a possible megastructure. There were rapid papers, heated debates, new observations, and careful modeling. Hypotheses rose and fell as each new dataset came in. Alien engineering was not dismissed out of habit, it was tested, and step by step, outcompeted by a natural explanation. So it's time to find out the truth about why this matters for tomorrow. Tabby's star trained us. It showed astronomers what to look for, which instruments to bring to bear, and which seductive shortcuts to avoid. The next time we see an anomaly that defies every dust model, every stellar glitch, every known kind of planet and atmosphere, we will approach it with sharper tools and a stricter checklist. And if that future signal still refuses to fit the natural universe, even after all of that, what happens next? What counts as an alien megastructure, really? So if we ever reach that point, what would we actually be claiming? What counts as an alien megastructure, really, in the hunt for alien life? It should be noted that when astronomers say alien megastructure, we are not imagining a single, smooth metal shell wrapped neatly around a star like gift paper. Instead, we are talking about a whole family of gigantic engineering projects: Dyson swarms, partial Dyson spheres, stellar engines, vast orbital habitats, all sharing one core idea, structures so large that planets start to look small beside them. So, let's begin with the most famous member of that family, the Dyson sphere. In popular culture, it is often drawn as a rigid ball enclosing a star, but while that picture is dramatic, it is also misleading. Freeman Dyson's original idea was much more practical. He imagined countless individual collectors and habitats, each in its own orbit, forming a loose swarm that intercepts a significant fraction of the star's light. This means the civilization harvests enormous power and then has to dump the waste heat somewhere. Where does it go? Into space, as infrared radiation. From far away, such a system would not look like a normal star at all. Its visible light could be strangely dim for its mass, as if something is blocking or absorbing it, yet the same object would glow unusually bright in the mid-infrared, like a furnace wrapped in a thermal blanket. In the data, we would not see the collectors themselves, but we would see their fingerprints in the star's astronomers' energy budget. But that is only one way to notice something unnatural. If parts of a swarm pass in front of the star from our line of sight, they would carve out bizarre shadows. Instead of the smooth, periodic dips we expect from a round planet and its atmosphere, we might see irregular, jagged, or even non-periodic drops in brightness. Some dips might be shallow, others extremely deep, and the timing could drift in ways that dust clouds and simple orbital mechanics struggle to explain. Other megastructure concepts push the imagination even further. A Shkotov thruster, for example, is a stellar engine built from a gigantic mirror that gently pushes a star and its whole planetary system across the galaxy using light itself as thrust. Ringworld-like constructs would stretch all the way around a star in a single, vast band. Optimistically speaking, these ideas are speculative engineering, but their observational signatures are grounded, asymmetric shadows, concentrated waste heat, and oddly smooth, engineered spectra that hint at artificial materials. So it's time to find out the truth about what we would actually see. If you come across a plot where a star's brightness suddenly plunges in a way no ordinary planet, no dust cloud, no known stellar glitch can reproduce, or you see an infrared survey flag a star that radiates like a wrapped-up furnace, you now know why some astronomers quietly pause and ask, is this natural or built? And if one of those strange signals survives every natural explanation we can throw at it, how would the scientific community respond? Step by careful step. The instruments that could catch a colossal shadow, so who, exactly, would judge a shadow that might be artificial? In the hunt for alien life, our first witnesses are not people at telescopes, but machines quietly staring at the sky for years. Planet hunting missions like Kepler and TESS were built to find small, Earth-like worlds. They watch hundreds of thousands of stars at once, measuring their brightness over and over, waiting for the tiny periodic dips that reveal a planet in orbit. A normal transit might dim a star by 1% or less, like a gnat crossing a car headlight. But while they are tuned for these subtle signals, their continuous stare also makes them perfect for catching anything stranger. What if the dips are 10 or 20%? What if they are irregular, with no clear period at all? This is exactly why objects like KIC 8462852, also known as Tabby's star, briefly set the field on fire. Its light curve showed deep, chaotic dimming events that did not look like any simple planet or dust ring. It should be noted that Kepler itself could not explain the cause. All it could do was raise a cosmic eyebrow and say, something unusual is happening here. Once that suspicion is raised, the case moves to the ground. Large observatories and networks of smaller telescopes can swing into action quickly. They provide higher cadence light curves, catching every tiny up and down in brightness, and they can observe in different colors, from optical to near-infrared. This means astronomers can test whether the dimming is stronger in blue light, as you would expect from dust, or nearly colorless, as you might expect from opaque, solid structures. Independent teams on different continents can confirm that the effect is real, not just a glitch in one instrument, or an odd quirk of a single pipeline. Then, if the signal still looks truly bizarre, we bring in the flagship, the James Webb Space Telescope. JWST does not just measure brightness, it dissects starlight into a spectrum with exquisite precision, especially in the infrared where heat reveals itself. A genuine megastructure, like a partial Dyson swarm, should intercept starlight and re-radiate it as waste heat, glowing in the mid-infrared. JWST can search for that excess glow, and for strange absorption features that do not match any known gas or dust in a typical atmosphere. So it's time to find out the truth. Kepler or TESS raises the suspicion, ground-based telescopes corroborate the weirdness, and JST, along with future missions, delivers the verdict. In this cosmic courtroom, the energy budget and spectral fingerprints are the hard evidence. Optimistically speaking, if all of that data lines up with some exotic but plausible natural model, the megastructure idea dies with honor. But if every natural explanation fails, and the shadow still refuses to behave like anything we know, the artificial hypothesis would no longer be fringe speculation. It would become the leading explanation, and the entire conversation about our place in the universe would have to change. And if that happened, how would humans react when the verdict finally reads, not just a planet, but a work of engineering, natural weirdness, or artificial design? So if the verdict really leaned toward not a planet, but a work of engineering, what exactly would we be looking at? Because in the hunt for alien life, a megastructure forces us into a stark, uncomfortable choice. On one side, we have natural weirdness. Maybe this strange dimming is a chaotic swarm of comets in a long, eccentric orbit. Maybe it is an enormous disk of dust, or a tangle of rings around a hidden giant planet, or star spots drifting across the stellar surface in patterns we have not modeled yet. Stars can pulse, burp, and flicker in ways that still surprise us. The universe is creative. On the other side, we have artificial design, a Dyson swarm of collectors sipping energy from the star, layered rings of habitats, a stellar engine pushing the entire system through space. In plain language, we would be asking, are we seeing rocks, gas, and plasma behaving oddly, or the skyline of a civilization that has mastered power on a stellar scale? It should be noted that scientists are trained to push the first option as far as it can possibly go. History has been merciless to premature its aliens' claims. From canals on Mars to early whispers about Kick 8462852, every famous candidate has collapsed into dust, comets, or instrumental quirks once better data arrived. This means the professional bias is strong. If there is any remotely plausible natural model, that is the one that wins. So, let's begin the real detective work. Astronomers would throw every natural scenario at the light curve. Could a swarm of icy bodies, slowly disintegrating, reproduce each dip? Could a warped circumstellar dust disk explain the timing and depth? What about a ringed planet, or a chain of planets, or complex star spots on the stellar surface? They would cross-check different wavelengths, searching for the spectral fingerprints of dust grains, gas in the atmosphere of a hidden world, or even subtle instrumental artifacts. If a simple, messy, natural model fits the data, the case quietly closes. But while natural explanations are always preferred, they can be stretched to the point of absurdity. If, after years of new observations and refined models, every dust cloud must be placed with surgical precision, every comet swarm must be tuned to the day, and every star spot must conspire to mimic engineering, something flips. Optimistically speaking, the artificial hypothesis does not just become allowed, it becomes the simplest explanation left standing. So it's time to find out the truth. When the universe hands us a mystery that looks designed, how do we decide whether we have discovered new physics or new neighbors? And if the balance really tipped toward neighbors, what would the next piece of evidence have to look like? Tonight's roadmap, following the signal to its source to answer that, we need a plan. Not just more speculation, but a clear path from the first strange flicker of starlight to the moment the world realizes we are not alone. So, let's begin by setting the stage for the journey we are about to take tonight. And this is where we follow the evidence step by step in the hunt for alien life. But instead of staying on familiar ground with habitable planets and quiet red dwarf stars, we are going to chase something far more extreme, a possible alien megastructure. This means we need a roadmap. First, we will ask a very basic, but crucial question. What would an alien megastructure actually be in physical terms? We will break down ideas like Dyson swarms, shells of collectors in orbit around a star, and stellar engines that push entire systems through the galaxy. How would those look in real telescope data? Would we see smooth, deep dips in brightness, or a permanent infrared glow from all that waste heat? Before we can judge a headline, we need to know what we are even looking for. Then, we will slow down and walk through a single, hypothetical discovery, almost frame by frame. Imagine an astronomer at 2 a.m., staring at a light curve from a distant star, seeing a dip that is too deep, too irregular, to match any known planet. We will follow that signal from the first late-night email to colleagues, through checks with missions like Kepler and TESS, to a spectral deep dive with the James Webb Space Telescope. It should be noted that we have been fooled before, with cases like Tabby's star, so every step of this path matters. After that, we will move inside the scientific community itself. How does a wild idea survive peer review? Who demands more data, more models, more ways the universe could trick us without invoking alien life? We will trace how attentive this is weird becomes, this might be artificial, and, optimistically speaking, how it could finally cross the line into consensus. Finally, we will widen the frame to the entire planet. What happens when the verdict leaks into the news cycle? How do governments respond? How do religions interpret a civilization that can build on the scale of stars? And what do ordinary people do when a notification on their phone quietly says, "Confirmed alien megastructure"? By the end of this video, you should be able to see a headline about a possible alien megastructure and instantly know what that really means, how credible it is, and what chain of events is likely to unfold next. So it's time to find out the truth. Which role will you slip into as we go? The exhausted astronomer, the skeptical reviewer, or the person waking up to history? How to read the sky, light curves, waste heat, and cosmic footprints. If you were that exhausted astronomer staring at a strange plot at 2 a.m., what exactly would you be looking at? To follow the story of a suspected alien megastructure, we first need to learn how to read the sky the way astronomers do. So, let's begin with the most important picture you never actually see, a light curve. A light curve is simply a graph of a star's brightness over time. Each point is one careful measurement. When a normal planet crosses in front of its star, the light curve shows a clean, smooth dip, repeating every orbit like clockwork. The depth tells us the planet's size, the timing tells us the orbit, and the shape tells us about the alignment. It looks almost boringly precise. But while planets make tidy signatures, nature can be messy. Dust clouds, comet tails, or clumps of debris create dips that change in depth, length, and shape, with odd gaps and overlapping events. When astronomers first saw Kick 8462852, Tabby's star, its light curve plunged by up to 22% in irregular, non-repeating ways. That is far too much for an Earth-like planet. In the hunt for alien life, some people immediately whispered megastructure. The data, however, had more to say. This is where the idea of an energy budget comes in. A star of a given mass and temperature should radiate a predictable amount of energy at different wavelengths. This means we can compare its visible light to its infrared glow and ask, is anything intercepting that power? If a vast swarm of collectors were surrounding a star, the visible light might look strangely dim, while the star blazes in the infrared as those collectors radiate waste heat. It should be noted that this is exactly what a Dyson swarm would do, not magic, just thermodynamics. So we separate the clues into two broad families. Geometric signatures are about blocking starlight. Transits, dimming events, and strange light curves tell us that something is physically getting between us and the star. Thermal signatures are about what happens to the stolen energy. Infrared excess, odd spectral fingerprints, or a mismatch in the energy budget point to material that absorbs light and then glows with heat. Do we jump straight to aliens from one weird light curve? No. We first ask whether dust grains of different sizes, evolving comet swarms, or subtle stellar variability could produce the same pattern. With Tabby's star, careful searches found no strong infrared excess, strongly arguing against a giant, warm megastructure and favoring dust instead. Optimistically speaking, once we understand these cosmic footprints, we are ready to follow a real case. In the next part, we will walk step by step from the first odd dip through every test to the moment when the word artificial can no longer be avoided, when the data won't behave, a discovery story. So what does it actually look like when the universe refuses to fit our models? In the hunt for alien life, that story does not begin with a message. It begins with a graph. A few years from now, deep in the automated test pipeline, a single star is flagged. At first, it is just another entry in a long list of candidates. But while most stars show neat periodic dips as planets pass in front, this one is different. Its light drops by 30%. Then, 40%. The dips are jagged, asymmetric, and most unsettling of all, a periodic, no clean clockwork orbit. No simple eclipsing binary, just chaos. So, let's begin with the people who notice. A small team of astronomers pulls the raw data, frame by frame. They check for cosmic rays, they test for scattered light, for detector errors, for anything that might fake a dimming event. The signal stays. It should be noted that this is the first real moment of discomfort. If the instrument is innocent, the star itself is misbehaving. They reach backward in time. Archival surveys from ground-based telescopes and earlier space missions show the same object, quietly observed for more than a decade. Slowly, almost reluctantly, the star has been dimming, a percent here, a percent there, over years. On top of that slow fade sit those sudden, brutal drops in brightness, like something enormous drifting across the stellar disk with no regard for regularity. At this point, the story leaves one observatory and becomes global. Networks of ground-based telescopes, from Chile to the Canary Islands to Hawaii, coordinate to watch the star continuously. Night for one site is day for another, so the light curve becomes almost unbroken. Higher time resolution reveals finer structure inside the dips, sharp edges and plateaus that refuse a simple geometric explanation. There is still no obvious period, no repeating pattern that would let us say, comfortably, planet. So it's time to find out the truth the usual way, by trying every natural model we can imagine. Comet swarms are tested first. Long dusty tails could create asymmetric dimming, but the depth of the dips is extreme, and the long-term fading does not line up with simple reservoirs of debris. Clumpy dust rings explain the slow fade, but not the sharp, deep, short events. Giant ringed planets help with the shape of some transits, yet they should repeat on a stable orbit, and these do not. Star spots and magnetic cycles are modeled, but they struggle to produce abrupt 40% drops without leaving clear fingerprints in the star's spectrum. This means that, line by line, the usual explanations are crossing themselves off. Optimistically speaking, that is when the team writes the first paper. The title is cautious, almost dull, an anomalous dimming event 100% inconsistent with standard astrophysical models. Only in the final paragraph do they add a single, careful sentence about large-scale artificial structures, and that is the moment the real storm begins. Because what happens when the next telescope points at that star, and the data look even stranger? When the word artificial enters the paper inside the astronomy community, that single word, artificial, lands like a small explosion. Some of us lean in, eyes bright. Others quietly roll their eyes. But almost everyone agrees on one thing: this star is doing something genuinely strange. And the data deserve a second, independent look. In the hunt for alien life, this is the moment when excitement has to fight with discipline. No one can just accept one team's pipeline. So within days, groups from Europe, North America, and Asia download the public light curves. They run their own reduction codes, correct for different kinds of noise, and cross-check against other targets in the same field. If the anomaly vanishes in someone else's analysis, the story ends here. But it does not vanish. Instead, the same bizarre pattern appears again and again. Different telescopes, different detectors, different methods, yet the dips line up. The long-term dimming repeats. The timing remains stubbornly off from what a normal planet in orbit should produce. This means the community has to accept a first, uncomfortable conclusion. Whatever is happening around this star is not just a glitch, so it's time to find out the truth. And the first rule is, nature gets every chance before aliens do. New models appear almost overnight. Some teams simulate warped, clumpy dust disks with grains of different sizes scattering light in complex ways. Others propose exotic stellar pulsations, where the outer layers of the star swell and contract in irregular rhythms. Still others build baroque multi-planet systems, with rings, moons, and tilted orbits, all trying to carve out the exact same light curve without invoking intelligence. Here's the pattern interrupt. If you walked into a conference coffee break right now, you might not even hear the word megastructure. You would hear dust opacities, radiative transfer, and non-radial oscillations. It should be noted that this is not avoidance, it is self-defense. No one wants to be labeled the alien person too early in their career. But while reputations are on the line, so is the possibility of a civilization-level discovery. So, let's begin to understand the social tightrope. Senior scientists urge caution on public statements, while quietly encouraging students to stress test every natural model they can imagine. Younger researchers whisper after talks, what if none of these work? Optimistically speaking, that would be extraordinary. Realistically, most of us expect a very weird, but still natural, explanation to emerge. By now, a consensus forms on one key point: the existing data have taken us as far as they can. To distinguish dust from engineering, pulsations from structures, we need more wavelengths, higher precision, continuous coverage. The community rallies around a simple plan: get the star onto every major facility we can, including JEST and the largest ground-based observatories. Because the only way to decide whether artificial belongs in that paper is to let the next generation of telescopes stare straight into the mystery. JEST looks closer, the verdict on the star's energy. So what happens when the most powerful space telescope we have stares straight into that mystery? In the hunt for alien life, this is the moment where speculation has to face hard data. DREST is not a quick snapshot mission. The observing campaign is planned like a chess match. Multiple visits are scheduled across the star's orbit, some when it appears calm, others deliberately timed to predicted dimming windows. We want to see the system both in its normal state and when the weirdness is at its peak. So, let's begin with what Webb actually measures. Instead of visible light, DREST spreads the star's infrared glow into a spectrum, from the near-infrared, where the star itself dominates, out to the mid-infrared, where cooler material shines. This means we are not just watching dips in brightness, we are weighing energy. For a star of this type, models tell us very precisely how much light it should emit at each wavelength. Any excess in the mid-infrared hints that something is intercepting starlight and re-radiating it as waste heat, just as a Dyson swarm would. So what does the spectrum show? At first glance, it is almost boring. A smooth rise in the mid-infrared. No sharp lines, no obvious fingerprints of familiar dust grains or gas in a thick atmosphere. But while smooth looks simple, the numbers are not. When the team integrates the total energy, they find that roughly 20 to 30% of the star's light appears to be missing from the visible and near-infrared, and reappearing as a broad, cool glow. It should be noted that this is exactly the sort of energy budget we would expect if a vast structure were harvesting power and bleeding off heat. Naturally, no one writes aliens in the first draft. The group runs through every natural model they can. Could it be an unusually thick, cold dust shell in the outer system, like a swollen debris belt? Maybe, but then the dust has to be tuned to just the right size distribution to make that smooth, featureless excess. Could it be a background galaxy, perfectly aligned with the star, adding its own infrared light? Again, possible, but the galaxy would need a very strange spectrum of its own, and deep imaging fails to reveal any separate object. Optimistically speaking, if it is natural, it is also incredibly contrived. As each explanation is pushed to its breaking point, the language in internal memos starts to shift. Phrases like consistent with large-scale artificial energy collection appear, cautiously, as one option among several. So it's time to find out the truth. Is there any remaining mundane way out? Or are we staring at the first serious evidence of a civilization reshaping its star? From anomaly to announcement, how science says we're not alone, so what happens when the last normal explanation has essentially failed? Do astronomers just step up to a microphone and say, "We found aliens"? Not even close. In the hunt for alien life, the first rule is, do not trust the first result. The team that found the anomaly writes up everything, including the boring details. They post a preprint so the entire community can see the raw light curves, the calibration steps, the assumptions. Then, they do something that sounds strange at first. They actively invite other scientists to tear it apart. If a hidden bug, a misaligned detector, or a subtle bias can explain the signal, they want to know before the world does. Peer review becomes almost aggressive. Referees demand alternative models, stress tests, simulated stars. Independent statisticians rerun the analysis. It should be noted that the loudest voices in these early stages are often the biggest skeptics. That is not resistance to discovery. That is how science protects itself from wishful thinking. Meanwhile, other observatories quietly swing toward the star. A space telescope in visible light checks whether the dips repeat with the same pattern. Large ground-based mirrors watch for color changes that might hint at dust instead of structures. Radio telescopes listen for narrow-band signals or broadband noise that should not be there if this is just a dusty disk. If the geometry is right, even neutrino or high-energy observatories might join in, searching for exotic byproducts of advanced technology. This means the anomaly is no longer a single odd dataset, but a coordinated campaign across the electromagnetic spectrum. As the months pass, the language in the papers begins to shift. Early on, you see phrases like unusual transit morphology and currently unexplained dimming. Later, after repeated checks, the wording hardens, no known natural mechanism reproduces all observed features. Eventually, in the most careful way possible, sentences appear like consistent with large-scale artificial structures in orbit around the star. No one writes, "We prove aliens exist." Instead, they narrow the options until the artificial one is the simplest remaining. At this point, major agencies step in. Space agencies, national academies, and large observatories convene panels behind closed doors. They compare all available data, draft cautious statements, and coordinate with governments and international bodies. How do you tell 8 billion people that we may have found a civilization reshaping its star without sparking panic or wild conspiracy theories? So, let's begin to imagine that choreography, press releases prepared in multiple languages, media briefings, and clear explanations of what we know and what we do not. Finally, the announcement day arrives. A joint press conference appears on every major network. The lead astronomers sit under bright lights and say, very carefully, that the simplest interpretation of the data is a large-scale artificial structure orbiting a distant star. Optimistically speaking, it is the first hard evidence that we are not alone. But they remind us, science never deals in 100% certainty. So what crucial test still stands between this claim and true confirmation? And what if that final test fails? The day after, news alerts, markets, and midnight sermons, the crucial test is still ahead. But the universe does not wait for our careful committees. Within minutes of that press conference ending, our phones would vibrate on the table. Push notifications stack up, evidence of alien megastructure detected. News apps flash red banners. Live streams switch mid-story. Suddenly, every channel has the same image on screen. A distant star, a strange light curve, and a headline asking if someone has built a shell around their sun. Do aliens exist? There are few questions with more power to hijack the global news cycle. Social media feeds explode. Some people post awe-filled threads about Dyson spheres and Kardashev Type 2 civilizations. Others share doomsday warnings and grainy movie clips of invading fleets. Memes appear within an hour. Photoshopped Dyson swarms wrapped around our own star, Goldilocks zone jokes, and fake recruitment posters for the first megastructure tourism agency. But while the internet races ahead, governments move in a very different way. In the first 24 hours, there would almost certainly be emergency meetings in major capitals. National security councils ask a blunt question: does this change anything about our safety? Intelligence agencies quietly pull old study reports, scan for any unexplained radio signals from that same system, and assess whether the discovery hints at technology that could, even in principle, reach us. Publicly, leaders choose their words with extreme care. Some frame it as a triumph of human science, the moment our telescopes finally touched evidence of distant engineering. Others stress uncertainty and potential risks, describing the megastructure as a cosmic unknown that we must study before we celebrate. It should be noted that, in the hunt for alien life, language becomes strategy. Religious and philosophical reactions unfold just as quickly, but on different wavelengths. Some faith leaders step up to microphones and say this confirms what they always believed: creation is vast, and other intelligences simply widen the stage on which a divine plan plays out. Others, especially traditions centered on human uniqueness, wrestle in real time with what it means if we are not the only rational beings in the universe. Here comes a pattern interrupt. Many believers, though, simply stretch their worldview. If there are distant, created civilizations, then perhaps we are all part of a larger cosmic community we do not yet understand. So, let's begin to see how quickly that idea spreads. Markets certainly do. Space-related stocks surge. Launch providers, telescope manufacturers, satellite companies, even asteroid mining startups see sudden spikes. Think tanks publish overnight analyses. If someone can build a megastructure, what does that say about long-term energy use, climate control, or starlifting? This means funding agencies quietly reopen folders labeled SETI, infrared sky surveys, and space infrastructure, and they do not close them again. And then there's the personal level. Long after the breaking news banners fade, lights stay on in bedrooms around the world. People stare at their ceilings or out of apartment windows toward a random patch of sky that now feels different. Somewhere out there, builders of stars may be orbiting their own sun under an artificial night. So it's time to find out the truth. Have they ever, even once, noticed the pale young planet that has just noticed them? 1,000 years away? Strategy, caution, and cosmic humility. If they did notice us, what then? Because at the distances we're talking about, that question stretches across not just space, but time itself. Let's put a rough number on it. Suppose this alien megastructure orbits a star 1,000 light years away. This means every photon we collect tonight left that system around the time Vikings were crossing the Atlantic. Any change they made yesterday will not reach our telescopes for another millennium, and any reply we send back, earliest delivery, the year 3024. So, this is not a Hollywood first contact scene with blinking lights and instant answers. It should be noted that what we really have is a one-sided revelation, a fossil record of engineering. We are looking at what they were, not what they are. By the time our first hello arrives, their civilization could be more advanced, completely transformed, or gone. How do we plan for a conversation that may last longer than all of recorded human history? In the hunt for alien life, that delay turns communication itself into a strategic dilemma. Do we beam powerful radio or laser messages straight at their star, announcing that a young, noisy species has appeared in this part of the galaxy? Or do we stay quiet, treating their megastructure as a warning sign rather than an invitation? Some will argue that a species capable of rearranging a star must have solved war, climate, and resource scarcity and could be benevolent teachers. Others will counter that raw capability says nothing about ethics. A stellar engine could be the work of philosophers or conquerors, or something so indifferent that we are no more than background radiation. Optimistically speaking, we might decide to send carefully crafted messages while also hardening our own infrastructure, just in case the universe is less friendly than we hope. But while the contact question is emotionally charged, the technological implications are more concrete. If we can prove that such a megastructure obeys known physics, we suddenly know that star-scale engineering is not fantasy. It is a reachable, if distant, engineering target. This means fusion research, space-based solar power, and gigantic orbital industries stop being abstract future tech and become early training wheels for a much longer road. We might start to see our climate and energy problems not as final exams, but as the first quiz in a course on managing planetary and then stellar resources. A single planet, a single atmosphere, a single Goldilocks zone around a single star would feel less like our whole story and more like chapter 1, and that leads to the deepest psychological shift. Do we still think of ourselves as the main characters of the universe, or do we finally accept that we are a young species, entering a story that began billions of years before Earth-like worlds formed here? So, let's begin to imagine policy, philosophy, and science built around surviving long enough to join that distant cosmic conversation. Yet one question hangs over everything, and we will carry it into the conclusion. Does discovering a megastructure 1,000 light-years away make you feel safer because such builders are distant and maybe disinterested, or more exposed? Because now we know that galaxy shaping power is achievable by someone, somewhere, and perhaps, one day, by us. So what do we do if the sky says artificial? So if the sky really whispered artificial, what then? We have walked a long path to reach that question. We began with a lonely astronomer staring at a misbehaving light curve at 2 in the morning, a star dimming too deeply, too irregularly, not like a normal planet transit. From that strange pattern of dips, we unfolded the idea of alien megastructures, Dyson swarms sipping a star's light, vast stellar engines, galaxy-scale engineering projects that would flood space with waste heat. In the hunt for alien life, we then asked a simple but ruthless question. How would these things actually look in the data? It should be noted that we did not rely on imagination alone. We followed the trail from Kepler and TESS to giant ground telescopes and finally to JDUST. Reading not just visible light, but the infrared glow, where waste heat must appear if something is truly wrapping a star. So it's time to find out the truth about what that journey would really mean. First, science would move slowly. Initial excitement, then skepticism, then years of cross-checks. Dust models would be tested and broken. Instrument errors would be hunted and ruled out. Only when every natural explanation failed and JWST's verdict showed a clean, excess infrared signature that matched larger-scale engineering would we dare to say the simplest explanation is artificial. This means a scientific revolution. Overnight, Kardashev Type 2 civilizations would shift from thought experiments to case studies. Stellar physics, energy engineering, even our models of how long civilizations can survive in a dangerous universe would have to be rewritten. We would know, with data in hand, that turning a star into infrastructure is not fantasy, but a reachable point on some technological roadmap. But while that would be thrilling for scientists, the social shock could be far greater. How do religions, governments, and ordinary people react when we confirm that someone else has already crossed the gap we are only beginning to measure? Do nations compete to control the message, or form a global council for a single cautious response? Do we treat the builders as distant neighbors, or as a mirror forcing us to ask what we might become? Optimistically speaking, such a discovery might unify us around long-term goals, protecting our planet, expanding into our own Goldilocks zone, and building technologies that, one day, let us join the community of star-shaping species. Megastructures would stop being just science fiction eye candy and become a stress test for how we do science under extreme uncertainty, how we handle civilization-level news, and how we choose our future once we know what is physically possible. So, let's begin with you. If tomorrow's headlines announce strong evidence for an alien megastructure, what would you support? Sending a deliberate message? Staying radioscillant and just listening? Or focusing entirely on leveling up our own technology first, treating the discovery as a distant warning light on the road ahead? What does that choice say about how you see humanity's role in this cosmic system? Tell us in the comments which path you would choose and why. And if you want to explore these ideas further, watch our deep dives on the Fermi paradox and on Dyson spheres next, where we examine why the sky is so quiet and how star-spanning projects might really work. Stay curious and stay skeptical, because the next weird light curve might be another dust cloud, or the first unmistakable shadow of our cosmic neighbors waiting for us to answer. But if that shadow appears, and we finally know we are not alone, the real question will be, what kind of civilization will we decide to become before they ever notice us?